Welcome! In this session, we'll explore problem number 1254, titled Number of Closed Islands. This problem challenges us to analyze a grid and determine the number of closed islands areas completely surrounded by water. We'll discuss the problem, break it down into manageable steps, and explore different approaches to solve it. Let's dive in. In this problem, you are given a grid representing a map where each cell is either land, marked as 0, or water, marked as 1. An island is defined as a group of connected 0s, where connectivity is determined by moving in one of the four cardinal directions up, down, left, or right. A closed island is a special type of island that is completely surrounded by water on all sides, meaning no part of the island touches the boundary of the grid. Your task is to count how many closed islands exist in the given grid. The input will be a binary matrix, and the output will be an integer representing the number of closed islands. Let's look at some examples to see how this works in practice. For our first example, the grid is an 8x4 matrix where 1s represent water and 0s represent land. When we analyze the grid, we find two closed islands. The first island consists of the cells 1, 1, and 2, 1, and the second island consists of the single cell 1, 4. Both of these islands are completely surrounded by water, with no part of the island touching the boundary of the grid. Therefore, the output for this grid is 2, as there are two closed islands. In the second example, the grid is another 8x4 matrix. Here, there is only one closed island, which consists of the cells 2, 2, and 3, 2. While the grid does contain other land areas, none of these form closed islands because they touch the boundary of the grid. For example, the land cells on the left and right edges are directly connected to the boundary. As a result, the output for this example is 1, since there is only one closed island. Now, let's take a look at the third example. This time, the grid is a 7x7 matrix with a mix of land and water cells. The grid contains two closed islands. The first is a small single cell located at 3, 3, and the second is a larger region composed of inner cells that are completely surrounded by water. Notice that all other land cells in the grid are either part of this larger closed island or touch the boundary of the grid, making them invalid as closed islands. Hence, the output for this example is 2, as there are two distinct closed islands. When solving this problem, certain edge cases need to be considered. If the grid contains only water, meaning all cells are 1, the result will be 0 because there are no islands. Similarly, if the grid contains only land, with all cells as 0, the result is also 0 because a closed island requires water completely surrounding it. For very small grids, such as a 1x1 grid, a single 0 would not count as a closed island since it touches the grid boundary. Lastly, if all land cells in the grid are connected to the boundary, the result will also be 0 because none of the islands are enclosed by water. These scenarios illustrate the importance of carefully checking the boundaries and conditions for determining closed islands. To approach the problem, we first consider the brute force method. The intuition here is straightforward. We identify every island in the grid by visiting each cell and exploring connected components of 0s, which represent land. Using either depth-first search or breadth-first search, we traverse each island and check if it touches the boundary of the grid. If it does, the island is not closed, but if it's fully surrounded by 1s, we count it as a closed island. This approach ensures that every cell is visited, making its time complexity O, m*n, where m and n are the dimensions of the grid. However, it has a drawback. During each traversal, we repeatedly validate the boundaries, which leads to redundant computations. To address this inefficiency, we can optimize the process with what we call the boundary marking optimization. Here, the idea is to eliminate boundary-connected islands up front. Instead of checking boundary conditions during each traversal, we first traverse the grid's boundary and mark all 0s connected to it as visited. This leaves only the interior 0s, which can then be explored to count closed islands using DFS or BFS. This optimization ensures that each cell is visited at most twice, once during boundary marking and again during island counting, maintaining the same O, m*n, time complexity but significantly reducing redundant checks. The chosen strategy builds on the boundary marking optimization, leveraging its efficiency and clarity. The key observation is that any island touching the boundary cannot be closed. By eliminating these islands at the start, we simplify the problem to counting only fully enclosed islands. This approach uses a single DFS or BFS to traverse each connected component effectively. The aha moment here is realizing that pre-processing the grid simplifies the main problem, isolating the closed islands for easier counting. This strategy is not just efficient but also modular, as it separates the task of boundary handling from the actual island counting, making the solution easier to debug. While it introduces a pre-processing step compared to the brute force method, the benefits outweigh this trade-off. Boundary marking reduces unnecessary computations, and the in-place modification of the grid avoids extra space for tracking visited states. Ultimately, this approach strikes the perfect balance between simplicity, efficiency, and clarity, making it the ideal solution for this problem. The problem asks us to find the number of closed islands in a 2D grid. Here, a closed island is defined as a group of connected land cells, represented by 0s, that is completely surrounded by water cells, represented by 1s. This includes being surrounded by water on the boundaries of the grid itself. To solve this, we can break down the process into clear steps. First, we validate the input. If the grid is empty or null, we immediately return 0 since there are no islands to process. Next, we extract the number of rows and columns from the grid, which will be useful for navigating through it. Then, we define a helper function using depth-first search, or DFS, to explore connected land cells. This function checks whether a given cell is out of bounds, which would indicate that the island touches the boundary and is therefore not closed. It also ensures that water cells are correctly treated as valid boundaries. As we explore, we mark visited cells by changing their value from 0 to 1, and recursively check all 4 directions up, down, left, and right. If any part of the DFS traversal reaches an invalid state, such as touching the edge, we propagate that information back through the recursion to ensure the island is not counted as closed. After setting up the DFS helper function, we proceed to traverse the entire grid to identify closed islands. We initialize a counter, closed islands, to 0. This variable will track the number of closed islands we find. For each cell in the grid, if we encounter a 0 that hasn't been visited yet, we initiate a DFS starting from that cell. The DFS will determine whether the island is completely closed. If the DFS returns true, indicating the island is valid, we increment the closed islands counter. Once we've checked all cells in the grid, we return the value of closed islands as the final result. There are several key insights to highlight here. First, the boundary check is critical. Any island that touches the grid boundary is automatically disqualified from being closed. Second, modifying the grid in place by marking visited cells saves memory, as we don't need an additional data structure to track visited nodes. Finally, the recursive nature of DFS ensures that any invalid condition, such as touching the boundary, is propagated back up the call stack, so only completely enclosed islands are counted. The grid itself serves as the main input and is modified in place to mark cells as visited during the DFS traversal. This approach avoids the need for additional space to track visited cells. The DFS relies on the call stack to manage the traversal path, with a maximum depth proportional to the size of the grid. Rows * calls, in the worst-case scenario, such as when the entire grid is one large island. Moving to the complexity analysis, the time complexity is rows * calls, because each cell is visited exactly once. The space complexity is also rows * calls, in the worst case, due to the depth of the recursion stack. We also need to consider edge cases to ensure the solution is robust. For example, a grid that is entirely water should return 0, as there are no islands. Similarly, a grid that is entirely land but touches the boundary should also return 0, as no closed islands are possible. For small grids, such as a single row or single column, it's impossible to have a closed island, so the result should again be 0. To better understand the algorithm, let's look at an example grid where the inner cells represent a single closed island. In the example grid provided, we begin our traversal at cell 1, 1, which is a 0. We call the DFS function starting from this cell. During the DFS, we mark 1, 1 as visited by changing it to 1, and then explore its neighbors in all 4 directions. For instance, we move to 2, 1, 1, 2, and so on, recursively applying the same logic. The DFS ensures that all connected land cells are explored and marked as visited.
Once the DFS completes for this island, we confirm that it doesn't touch the boundary, so we increment the closed islands counter to 1.
As we continue traversing the grid, we find that all other land cells are either already visited or part of the same island. Therefore, the total count of closed islands remains 1. The final output for this grid is 1, signifying that there is exactly one closed island. Here, we start by defining a class called solution and within it, the closed island method. This method takes a grid as input, which represents a map of land and water where 0 indicates land and 1 indicates water. The first step is to determine the number of rows and columns in the grid using len, as this will help us navigate through the grid. Next, we define a helper function called DFS, short for depth first search. This function is crucial for exploring the grid and checking if a piece of land is part of a closed island. Inside the DFS function, the first condition checks if we've reached the boundary of the grid. If so, the island is not closed, so the function returns false. The second condition ensures that we stop the recursion if we encounter water or if the cell has already been visited, meaning it's been marked as 1. If the current cell is land, we mark it as visited by setting grid, RC, to 1. Then, we make recursive calls in all 4 directions, up, down, left, and right, to continue exploring the island. Finally, the function returns true only if all 4 recursive calls confirm that the island is closed, meaning it doesn't touch the grid's border. Outside the helper function, we initialize a variable closed_islands to 0, which will eventually hold the count of all closed islands in the grid. Now, we iterate through every cell in the grid using nested loops. The outer loop iterates over the rows, and the inner loop iterates over the columns. For each cell, we check if it represents land, indicated by the value 0, and if it hasn't been visited yet. If both conditions are met, we call the DFS function starting from that cell. If the DFS function returns true, meaning the island is closed, we increment the closed_islands counter by 1. Once we have visited all the cells in the grid, we return the value of closed_islands, which represents the total number of closed islands. This implementation efficiently combines grid traversal with depth-first search to solve the problem. Here, we start the Java implementation for the problem of counting the number of closed islands. First, we define a class called solution and within it, a method named closedIsland. This method takes a 2D grid as input, representing the map of land and water, and it will return the count of closed islands. We initialize variables for the number of rows and columns in the grid, as well as a counter closed islands to keep track of the result. Next, we define a helper method called DFS that performs a depth-first search. The purpose of this method is to check whether an island is closed by recursively visiting all connected land cells. To begin, we handle the base case. If the current cell is out of bounds, meaning it's beyond the edges of the grid, we return false because that would indicate the island is not closed. Then, we check if the current cell is already water or has been visited. If so, we stop recursion by returning true. Otherwise, we mark the current cell as visited by setting its value to 1. After that, we recursively call the DFS method for all 4 directions, up, down, left, and right, to explore the entire connected component of the island. The next step in the helper method is determining whether the island is closed. To do this, we return the logical end of the results from visiting all 4 directions, top, bottom, left, and right. If any of these directions is not closed, the method will return false, meaning the island is open. With the helper method in place, we now traverse the entire grid using nested loops. For each cell, if the value is 0, which represents land that hasn't been visited, we initiate a DFS from that cell. If the DFS determines the island is closed, we increment the closed islands counter. This ensures that every closed island is counted exactly once. Finally, after traversing the grid, we return the total count of closed islands. This implementation efficiently identifies and counts all closed islands using a combination of DFS and grid traversal. To solve the problem of counting closed islands, let's start with a simple example. Here, the input is a 4x4 grid, and the first step is to initialize some variables. We set rows and calls to represent the dimensions of the grid, and closed_islands is initialized to 0 to track the count of closed islands. The next step is to iterate over each cell in the grid. As we do so, we encounter our first land cell at grid 1, 1. This is where we begin our depth-first search to determine whether this land area forms a closed island. Once we identify the first land cell at grid 1, 1, we start a depth-first search by calling DFS 1, 1. In this process, we mark the current cell as visited by setting grid 1, 1 to 1. Now, we explore all four directions from this cell. When we go up, calling DFS 0, 1, it returns true because the cell is water or out of bounds. Moving downward, the DFS continues to grid 2, 1. From grid 2, 1, we repeat the process, marking the cell as visited, and exploring all directions. Each recursive call either hits water or continues exploring the island. Once all directions are fully explored and return true, it confirms that the island is closed. We then increment closed_islands by 1. After completing the traversal, no other unvisited land cells are found, so we finish with a final count of closed_islands equals 1. Now, let's look at a different example where the island is open. Here, the grid is smaller, with dimensions 3 by 3. We initialize rows, calls, and closed_islands similarly to the previous example, starting with a count of 0. As we iterate through the grid, the first land cell we encounter is at grid 0, 0. We begin a depth-first search at this cell by calling DFS 0, 0 and marking it as visited. From here, the DFS explores all four directions. When exploring from grid 0, 0, the DFS call to the top DFS -1, 0 returns false because it's out of bounds. The remaining directions return true, but because one direction leads to the grid's border, this indicates the island is open. Since the island is not closed, we do not increment closed_islands. The search continues, but no other closed islands are found in the grid. The final count remains closed_islands equals 0. Now, consider a slightly more complex example with a mix of both closed and open islands. In this mixed example, the grid has dimensions 4 by 5, and we initialize rows, calls, and closed_islands as usual. We begin iterating through the grid and encounter the first land cell at grid 1, 1. A depth-first search explores all directions from this cell, marking each visited land cell and fully traversing the island. Since this island is closed, we increment closed_islands to 1. Continuing the search, we find another land cell at grid 1, 3. A DFS traversal determines that this island is open, so we do not increment the count. After traversing the entire grid, the final count of closed islands is closed_islands equals 1. The time complexity of our solution is primarily influenced by the depth-first search, or DFS, operations conducted over the grid. First, the algorithm traverses the entire grid using two nested loops, one iterating through rows and the other through columns. This outer loop ensures that every cell in the grid is visited once, resulting in m*n iterations, where m represents the number of rows and n the number of columns. Now, every time we encounter a land cell, which is represented by grid r(c) == 0 and hasn't been visited, we initiate a DFS traversal. During this process, we explore the entire connected component of land, marking each cell as visited to avoid revisiting it later. Importantly, each land cell is visited only once across all DFS calls. Therefore, the total time spent on all DFS traversals is proportional to the number of land cells, which is also at most m*n. Combining the outer grid traversal and the DFS operations, the overall time complexity of this solution is m*n. Now, let's analyze the space complexity of the solution, which depends on two main factors: the grid storage and the recursion stack utilized by the DFS. First, the grid itself is stored in memory, and since we modify it in place to mark visited cells, no additional space is needed for a separate visited array. Hence, the grid's space usage is m*n. Next, the recursion stack comes into play during DFS calls. The depth of the recursion stack is proportional to the size of the largest connected component of land. In the worst-case scenario, where the entire grid is land, the recursion stack depth can grow to m*n. As a result, the overall space complexity is determined by the grid and the recursion stack, both of which can require m*n space in the worst case. Now, let's compare this approach to other potential methods. A naive or brute force approach to count closed islands might involve explicitly copying the grid and checking all possible subsets of cells to identify closed islands. This would result in an exponential time complexity, making it computationally infeasible for larger grids. By contrast, the DFS-based approach we've implemented is far more efficient, as it leverages in-place marking of visited cells and avoids unnecessary recalculations. Looking at the best and worst cases, if the grid contains no land cells, meaning all cells are water, only the grid traversal occurs, and the complexity is reduced to O(m*n), with no DFS calls. On the other hand, if the entire grid is land, the time and space complexity reach their maximum at O(m*n), as every cell contributes to DFS traversal and recursion stack depth. Mathematically, each cell is visited exactly once either during the grid traversal or as part of a DFS call. This ensures the overall time complexity remains O(m*n), while the recursion stack depth is limited by the size of the largest connected component, which also caps space complexity at O(m*n). To summarize, the time complexity of this solution is O(m*n), where m and n are the grid dimensions. This is because each cell is processed exactly once, whether during the grid traversal or during DFS exploration. The space complexity is also O(m*n), which is dominated by the recursion stack in the worst case, when the grid is entirely land. This approach is optimal for solving the problem, as it minimizes both time and space usage while ensuring accuracy and efficiency. When solving the number of closed islands problem, there are several common mistakes to watch out for. First, not marking visited cells during traversal can lead to revisiting the same island multiple times, which wastes time and can even cause infinite loops. Always use a visited matrix or modify the grid itself to track which cells have already been processed. Second, boundary checks are critical. If your DFS or BFS logic accesses grid indices without ensuring they're within valid bounds, you risk index out-of-bounds errors. Always verify that the row and column indices fall within 0 equals I rows and 0 equals J calls. Another frequent issue is misidentifying surrounded islands. Remember, an island that touches the grid boundary is not closed, so you must explicitly check all edges to ensure the island is fully surrounded. Inefficient grid traversal is another pitfall. Recomputing connected components without memoization or a proper visited mechanism can lead to redundant work. Lastly, watch out for the problem's connectivity rules. If only vertical and horizontal connections are allowed, including diagonal neighbors in your traversal will result in incorrect solutions. Always confirm the rules before starting your implementation. Now, from an interview perspective, this problem is an excellent opportunity to demonstrate your understanding of connected components. The grid can be visualized as a graph where cells are nodes and valid neighbors or edges, making techniques like DFS, BFS, and union find highly applicable. When preparing, consider edge cases such as empty grids, grids with no water or no land, single row or column grids, and islands that touch the boundary. These scenarios often trip up candidates. It's also important to understand the trade-offs between approaches. While recursive DFS is simple and quick to write, it can cause stack overflow on large grids. Iterative BFS avoids this risk but requires additional memory for the queue. Union find is efficient, especially for dynamic updates or repeated queries, but it can be more complex to implement. During interviews, it's crucial to communicate your assumptions clearly. For example, clarify whether diagonal connections count, whether you're allowed to modify the grid, and the constraints such as grid size. This ensures alignment with the interviewer and avoids misunderstandings. This problem also has strong connections to other popular grid-based problems. For example, number of islands, LeetCode 200, asks you to count the number of islands in a grid, while surrounded regions, LeetCode 130, involves identifying and capturing regions of O completely surrounded by X. Max area of island, LeetCode 695, focuses on finding the largest island, and flood fill, LeetCode 733, requires you to implement a flood fill algorithm. These problems share similar traversal techniques and are great for practicing grid-based DFS, BFS, or union find approaches. Speaking of approaches, the problem can be tackled in multiple ways. Recursive DFS is simple and often the go-to method for many. However, it risks stack overflow on large grids. Iterative BFS avoids that issue and can be easier to visualize for some, though it does require more memory for the queue. Union find is another option, particularly useful for scenarios involving dynamic updates or multiple queries, but it tends to require a deeper understanding and is less intuitive for beginners. Lastly, modifying the grid directly allows you to save memory by avoiding a separate visited matrix, though this approach isn't always allowed depending on the problem constraints. That said, modifying the grid directly does come with its own trade-offs. While it can save memory, this method may not be permissible if the grid is immutable or if the problem explicitly requires preserving the original input. Always check the constraints and requirements carefully before deciding on this approach. Balancing simplicity, efficiency, and adherence to problem constraints is key when choosing the right solution for the number of closed islands problem. Great job! To wrap up, we reviewed the number of closed islands problem, summarized its key elements, and discussed the importance of DFS and BFS for tackling grid-based problems. Remember to practice regularly and stay consistent in your coding journey. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!